The Xenon N-ton and Panda X direct detection dark matter experiments have just reached a mind-boggling level of sensitivity. Today we will come to understand how these experiments search for dark matter, how their extreme sensitivity now represents a new hurdle in that search, and how scientists can penetrate the neutrino fog to continue to look for the most feebly interacting particles in our universe. It is not always easy to see through the fog. Fog stymies, fog obscures, fog hides. It's easy to see hints of people, objects, fears that may not exist. And it's just as easy to miss something vital. This sentiment carries over into the world of particle physics. If dark matter consists of particles, those particles must interact extremely weakly with matter, and hence our detectors. Otherwise, we would have captured them already. So hunting down dark matter will likely require us to search for particles that interact more weakly than any we have ever observed. That raises a problem. If dark matter triggers our detectors less frequently than other particles, those other particles can swamp the signals produced by dark matter interactions and leave us looking for the proverbial needle in a haystack. And as dark matter search experiments become ever larger and ever more sensitive, the list of particles they can capture expands. This month, two cutting-edge dark matter direct detection experiments, Xenon N-ton and Panda X, reported that they have reached an exquisite level of sensitivity and added an extra hurdle to the search for dark matter. These experiments have captured the scattering of solar neutrinos off the xenon atoms in their detection tanks. The detection of neutrinos is a feat usually reserved for more massive Cherenkov water detectors, such as Super Kamiokande. These results are a massive step forward in the field of direct dark matter detection. Direct detection dark matter experiments have finally become stable enough and sensitive enough to capture neutrinos, particles that penetrate the entire Earth without interacting. However, this realization is bittersweet. Given that we have not found particulate dark matter yet, it must, if it exists, interact even more weakly with our detectors than the solar neutrinos that are streaming through those detectors constantly. That means that these solar neutrinos now represent a new background for direct dark matter searches. They're particles that swamp our detector and cannot be blocked by any viable thickness of shielding. This milestone in direct dark matter detection used to be called the neutrino flaw, a hard limit that dark matter physicists would find it very difficult to go beyond. Now, many prefer the term neutrino fog, a challenging, obfuscating barrier that will make our searches lengthier and more difficult, but which can be overcome with the right approaches and the right technology. It appears that if we are to detect dark matter directly, we will need to find ways to peer through the gloom of the neutrino fog.